Dear friends, welcome to my video. Kindly click on the CC button for subtitles. Quantum tunneling, a cornerstone principle of quantum mechanics, is a phenomenon that, at first glance, appears to contradict our everyday experience of the world. Yet, its relevance and practical application in various aspects of our lives and technology is undeniable. At the heart of quantum tunneling lies the probabilistic nature of quantum mechanics. Unlike classical physics, where particles are restricted by energy barriers they cannot overcome, in the quantum world, particles can tunnel through these barriers despite not having sufficient energy in the classical sense. In essence, particles can be found on the other side of a barrier where, according to the laws of classical physics, they should not be. One of the most practical real-life applications of quantum tunneling is in the field of electronics, specifically in the operation of tunnel diodes and scanning tunneling microscopes (STMs). Tunnel diodes, also known as Esaki diodes named after the Japanese physicist Leo Esaki, who received a Nobel Prize for this work, operate on the principle of quantum tunneling. Unlike standard diodes, they exhibit negative resistance, allowing them to switch on and off at incredibly high speeds. These diodes have been instrumental in the development of high-frequency electronics used in a wide range of technologies, from telecommunications equipment to space probes. Similarly, STMs also harness quantum tunneling, but in a distinctly different manner. By bringing a sharp metal tip incredibly close to a surface, electrons tunnel through the minuscule gap, producing a current. By measuring this current, scientists can map surfaces at the atomic level. This has opened doors to the detailed study of a plethora of materials, surfaces, and nanostructures. In the natural world, quantum tunneling is no less present. An exquisite example is seen in the Sun and other stars. Here, quantum tunneling allows hydrogen nuclei, or protons, to overcome the colossal electromagnetic repulsion to fuse together, forming helium and releasing the vast amounts of energy we experience as heat and light. Without quantum tunneling, these nuclear fusion reactions would not occur at the rates we observe, and life on Earth, which relies on sunlight, would likely not exist as we know it. Another remarkable example of quantum tunneling in nature can be found within our own bodies. Enzymes, the biological catalysts that speed up chemical reactions in cells, exploit quantum tunneling to enable reactions to occur at a much faster rate than would otherwise be possible. Recent research has indicated that without quantum tunneling, many biological processes would be too slow to sustain life. In the world of computation, the concept of quantum tunneling holds the promise of a revolution. Quantum computers utilize quantum bits, or qubits, that can represent 0 and 1 simultaneously due to a quantum phenomenon known as superposition. Furthermore, qubits can also tunnel between different states, providing the basis for quantum computation, which could vastly exceed the power of classical computers. While still in its nascent stage, quantum computing is rapidly advancing and is poised to transform many sectors, including cryptography, optimization, and drug discovery. The phenomenon of quantum tunneling might seem abstract and detached from our everyday reality, but it is instrumental in the operation of various technologies and natural processes that form the backdrop of our lives. It illustrates how the bizarre and counterintuitive world of quantum mechanics underpins our existence and our technological progress. As our understanding of quantum mechanics deepens, we can expect even more practical applications of phenomena like quantum tunneling in the future. Thank you for watching my video. Kindly subscribe to my YouTube channel and give a thumbs up. Thanks for your support.